Alright, so in this video I'm gonna be explaining another important article about domain adaptation. The title is Domain Generalization under Conditional and Label Shifts via Variational Bayesian Inference. This paper in 2021 from National University of Singapore. So we propose a domain generalization approach to learn on several label source domains and transfer knowledge to a target domain that is inaccessible in training. It means that even the samples are not accessible. We know that in unsupervised we never use labeled data, but here not only we don't use labeled data, but also we don't use the samples, the sentences itself. So considering the inherent conditional label shifts, we could expect the alignment of probability of X given Y and probability of Y. However, the widely used domain invariant feature learning relies on aligning the marginal concept shift. We have three different domain shift: concept shift, covariate shift, and label shift, and it's very hard to decouple these things. However, the widely used domain invariant feature learning relies on aligning marginal concept shift, which rests on unrealistic assumption that probability of your label is invariant across domains. We thereby propose a novel variational Bayesian inference framework to enforce the conditional distribution alignment with respect to probability of X condition on Y via the prior distribution matching in a latent space, which also takes the marginal label shift with respect to P of Y into consideration with the posterior alignment. Extensive experiments on various benchmarks demonstrate that our framework is robust to label shift and cross-domain accuracy is significantly improved, thereby achieving superior performance over the conventional counterparts. So in the proposed method, we are assuming that the probability of source is different from the unknown target, probability of the label of the unknown target. And we have this inference graph that X is affecting Y and Y is affecting Z. And we are dealing with multiple source domains. So the difference between domain generalization and domain adaptation, of course both of them are unsupervised, we don't use labels of target, is that domain generalization, the target is unknown. We don't use it for training. We don't use the samples for training. But for domain adaptation, we use the target samples for training. For example, we do pseudo labeling and do many different paradigms. So assuming that there is no concept shift, so the probability of source and target of label condition on f of x is the same and label shift also the same, and given the Bayes theorem, so we is able to align P if their probability is the same. However, the label shift, for example, class imbalance, in some sources we have more classes of one type, in another source or target we have a different distribution. So it's quite common in domain generalization. Since f is deterministic mapping function, this f that I said to encode, f is deterministic mapping, is able to encode the domain invariant representation under covariate shift assumption. Under the label shift, the covariate alignment cannot be used as an alternative of conditional alignment. So there are three contributions. They explore both conditional label shift in various domain generalization tasks, investigate limitation of conventional methods under different shift assumptions. Then they propose a practical and scalable method to align the conditional shift via the variational bayesian inference. Then the label shift can be explicitly aligned by the posterior alignment operation. So you see different kinds of domain shift like label shift, covariate shift, concept shift. Some people talk about conditional shift as well. So the conventional IFR assumes that P of y and P of y conditional on X are invariant across domains. Since f is a deterministic function, should also be invariant across domains. Therefore, P of X of different domains are aligned. The conditional shift is also aligned. So this is an illustration of the framework, consists of a conditional encoder F that we were talking about, this F, this conditional feature encoder. So we give our images to this conditional encoder, a domain-wise likelihood maximization network, a label prior network. We have a label prior network, a classifier, and a classifier, this classifier here. And our label, our latent representation Z, this latent representation that you see a Gaussian here, this latent representation is aligned with the Gaussian prior. So we have this prior network, LLPP stands for prior. Now we are using this to get this latent variable, latent representation, to design law such that it is aligned with the prior. So to align the class dependent across different domains, we first construct its approximate Gaussian distribution and resort to the variational Bayesian inference to bridge it with a simple Gaussian family for which the inference is tractable. So the proposition says the minimization of interdomain conditional shift is achieved when its approximate distribution is invariant across domains, and the KL divergence between P and Q is minimized. So you see a simple justification that if we have KL divergence of them, the pair is 0, then we have the KL divergence of P1 and P2. So Q1, P1, Q2, P2, Q1, Q2. So we infer that P1 and P2 should have the KL divergence between them should be 0 as well. And following the variational bound, minimizing the KL divergence is equivalent to maximizing this elbow of the elbow stands for evidence lower bound. I've explained them several times in the context of autoencoder, variational autoencoder. And so This d of KL is again KL divergence of approximate from the true the posterior. And the elbow of the likelihood can be written like this. This E is expectation, so Z is drawn from this distribution Q. So by further incorporating the second objective into this equation 3, we attempt to minimize the KL divergence of P and Q, and then P sub I should be invariant across source domains. The first optimization objective, this one, targets to align the conditional distribution across the source domains. Since the prior distribution is the multivariate Gaussian distribution, it is also natural to configure Q as multivariate Gaussian. Practically, we follow that reparametrization trick of variational. This very popular paper in 2013. They introduced the idea of reparametrization in such a way. They followed that in such a way that the inference model has two outputs, mu sub j and sigma sub j, which are mean and variance of the Gaussian distribution. So because this is mean and this is the variance, then you get the latent variable. So the loss is as simple as this. The second optimization objective aims to maximize the probability of observing the input x given y and z. It maximizes the likelihood that the latent feature representation of images in a specific domain can effectively represent the same class images in the domain. Practically, our F contains n sub-branches, each of which correspond to a domain. So we have n sub-branches, and you see I is passing from 1 to n. So for different branches, for different domains, we should do the same thing. Still the same measure, which solves the maximum likelihood by minimizing the difference between input data and the generated data in the corresponding domain. And this F is only used in training. Posterior collapses is a long-lasting problems of variational autoencoders. So the recent progress of discrete priors or flow model can be potentially added on our model. However, our training does not suffer from this posterior collapse. Note that each of the n decoder is only trained with about 1 over n data of encoder F, and it is likely that the weak decoder can also be helpful. Using an approximation with multivariate Gaussian prior offers much better tractability as in variational autoencoder, which is good for posterior modeling. So we calculate the loss functions, and then we update the parameters according to gradients. And then we have label prior. Inferencing latent representation requires to know the label information in advance. Since we are modeling the approximate conditional distribution, although y is always available in training, the ground truth is not available in testing. We note that F sub LM is only used in training, which always has y, has the label. To alleviate this limitation, we infer the label from the input image X as a prior to control the behavior of the conditional distribution matching module. Specifically, we configure the label prior network to infer the pseudo label and use y hat as input to the posterior label alignment classifier in both training and testing. Moreover, at the training stage, we can further utilize the ground truth y and minimizing the KL divergence between Q of z condition on x and y and condition on x and y hat to update the encoder. Finally, we aligned this probability of y to obtain final classifier. Since the classifier is deployed on all source domains, we can regard all the source domains as a single domain and denote this classifier where P is class conditional latent representation and P hat of f of x is its label distribution. Suppose that all conditional distributions and the latent distribution are aligned to each other using variational Bayesian inference. They should also be aligned with P hat. Therefore, the posterior alignment and final prediction of the sample from domain I can be reformulated like this. And this term is the case element value of the classifier's softmax prediction. So you see the KL divergence between L and S. When we go from this source to this target, the accuracy drops when the KL divergence between them increases.